The SN2 reactions will require a strong nucleophile. So what are the characteristics of a strong nucleophile? One is that they will have a negative charge. So we would expect that that is a better nucleophile than water. Also, strong nucleophiles are polarized atoms. So they're going to be the larger atoms are going to be better nucleophiles. Okay, so here are the listing of strong nucleophiles. You'll notice they all have a negative charge. You've got the halogens with the exception of fluorine. You've got sulfur with a charge, oxygen with a charge, carbon with a charge. SN2 reactions are also very affected by the solvent that they're in. A polar solvent is required for these reactions because you have a negatively charged nucleophile and you need a polar solvent to keep it in solution, to solvate it. You need polar solvent to solubilize, to keep it in solution. It also stabilizes the transition state. Polar solvents come in two different varieties. They come as protic solvents. These are solvents that are able to hydrogen bond. These have something, an oxygen attached to a hydrogen, or they might have a nitrogen attached to a hydrogen. So these are able to hydrogen bond, the protic solvents. These are water, methanol, ethanol, ammonia, acetic acid. Aprotic solvents are polar, but can't hydrogen bond. And of course, protic is a proton, so aprotic means they don't have a proton that can hydrogen bond. And this would be things like acetone, DMF, DMSO, acetonitrile, and HMPA. SN2 reactions are much faster in polar, aprotic solvents, and we will see why after we look at the differences here. So here we have our nucleophiles. These are all halogens, and we'll see that if we put them in an aprotic solvent, the iodine increases 150 times, 221,000 times, and 82 million times for the fluorine. So it makes a big difference whether you have it in a protic or an aprotic solvent. And this is why. If we're in a protic solvent, the lone pairs on the oxygen are going to stabilize the positive charge here. No surprise there. If we have a negative ion, the hydrogens stabilize the negative charge. So both ions are stabilized. With an aprotic solvent, move it up a little bit, it's polar, so this positive charge has been stabilized. But the negative charge is not stabilized. it can't, the positive charge that would stabilize it is hidden inside this molecule. It's not accessible, and so it's not stabilized. This does a couple of things this does. One is it keeps this naked so that it's not surrounded by a solvent shell. It makes it easier for it to get into, attack the atom that it's after. And it doesn't have a big solvent shell around it. The other thing is it puts it at higher energy. So if we look at the potential energy of our nucleophile in a protic solution, its energy is down here because it's stabilized. In an aprotic solution, the energy is up here, so that makes the activation energy much less. So let's look at the following reactions and see which one is going to work at a faster rate. Well, the only real difference in these two reactions is the water versus the DMSO. So we're just comparing solvents. And we know that this SN2 reaction will happen faster. Occur faster in the DMSO, in the aprotic. Well, then let's look at these two down here. The only difference is the nucleophile. So which nucleophile is going to be more effective? Well, we said that larger molecules are better nucleophiles because they're more polarizable. So we would expect this one. Iodine is larger and a better nucleophile. This next section, 7.5, is very interesting. It's certainly worth reading, but we're not going to discuss it here, unfortunately.